So thank you so much for joining today's workshop webinar from CTSA, University of Florida, and Florida State University Clinical and Translational Science Award. And we're part of the statistics, biostatistics, informatics, and research design program. And my name is Zhou He. I'm currently a professor at FSU School of Information. I'm also the director for the Institute for Successful Longevity. I've been here for about 11 years, and this is my seventh year being part of the CTSA effort, and I have been leading the informatics team here. So today with me, I have Dr. Balu Basudan, who is also currently a research faculty at School of Information, and he's also part of the CTSA BIRD team, working with me closely on providing informatics education, training, and resources to our faculty and students. So yeah, Balu, do you want to say a few words about yourself?
Yeah, sure. Thanks. Yeah. Hi, everyone. Nice to meet you all. I am Balu Basudan, currently a research faculty at School of Information at CCI. I'm part of CTSA Bird team here and works at Dr. Head in the eHealth lab here at School of Information. Looking forward to the
Great.
talk.
Thank you so much. So today we have a pretty packed schedule. So this webinar is supposed to be like 90 minutes. So we have about 20 minutes or so general brief introduction about generative AI in medicine and healthcare. And then we'll give you a very fine-grained, detailed instruction tutorial on how to build health agent using LangChain and LangGraph, which are two major open source frameworks for building agent models with open source or closed source language models. But before that, I want to give you a quick introduction about our team. So as I mentioned, CTSA is supported by the National Center for Translational Sciences, National Center for Advancing Translational Sciences. So we had our previous round of CTSA funding from 2019 to 2026. And we just 2025, and we just started a new 7-year cycle funded by a new round of UM1 funding from CTSA. So I'm currently co-leading this team with my collaborator and a colleague, Dr. Jyoti Sinha from Department of Statistics. And I'm the lead for informatics, mainly focused on providing resources and education, and also research support on accessing health data, human health data, including electronic health records, including national health surveys. So we have been supporting access to data such as One Florida Clinical Research Consortium's One Florida Data Trust, also all of us national cohort and also national cohort for COVID-19 research called N3C. So we have really helped a lot, like trying to build all this, not only the training resources, but also the infrastructure to support researchers. We have been constantly looking for open source, open access resources and data that are available to us, and create the data usage agreement or institutional data usage agreement for those resources. And so we're now providing 4 major data resources, including N3C, National Cohort Collaborative, COVID Cohort Collaborative, all of us, One Florida, and also there's another data set called Critical, which is provided by my colleague, Dr. Yuan Luo's consortium at Northwestern University, which includes 6 universities, critical care and ICU data in the central data warehouse. And we have also a very wonderful team in our core, including both researchers and scholars from statistics, qualitative research, and also informatics field. So we provide also grant development support. So if you are interested in developing a research grant that includes a biostatistics or informatics component in it, please feel free to reach out to us by submitting a ticket to our FSU Health ticketing system to our team. So we'll be able to help you providing 1-hour free consultation services and also providing ongoing support to your projects or plan proposal. So these are some of just a list of the resources and how the services we're providing to researchers here: clinical translational research design, biomedical informatics database access, informatics and data analytics, data analysis, qualitative, power analysis, data analysis plans, statistical design for proposals, data cleaning, and survey development. We also, as I mentioned, like the major resources are One Florida Data Trust, which includes electronic health record data, Medicare, Medicaids, and also cancer registry for over 20 million patients. And now they're expanding One Florida data to include data from University of Alabama, Birmingham, Emory University, University of California, Irvine, University of Minnesota. So it's called One Florida Plus. I think so far the number has been drastically increased over from 20 million, to 27 million patients over the past 10 years. So it's a really rich resource. And all of us, some of you already have been using all of us. It's a national cohort developed by National Institute of Health. So they have invested fairly significant money to improve precision medicine research. So that was an initiative started in 2015. So now all of us is provided to researchers as a resource. So people here can use that using your FSU credential because we have the data usage agreement between FSU and the NIH on this particular resource. And also we have right now still providing our informatics and biostatistics training materials through our Canvas website. So this is a self-enrolled Canvas site. So you just have to type this URL to your browser, so you'll be directly redirected to this Canvas website, which provides you with access of the previous resources we developed. So essentially, we develop resources about how to use One Florida data for research, and also some of our previously provided training workshops on these resources. So we're now really moving these resources to a more more integrated resource with other health services and health sciences research provided by other teams of CTSA. So please be on the lookout for information about the upcoming resources provided by CTSA. And also, if you're interested in learning more about CTSA, please feel free to check out our website, ctsa.fsu.edu, which was recently created. It's a revamp of a previous website, which provides all the resources. And as I mentioned, we are really trying to help researchers, with their translational science research and the clinical research. So if you're interested in getting help from us, especially for community engagement type of research and also clinical research, and also if you are junior faculty and are interested in learning about how to write NIH grants, especially for career development grants or research grant R1, R21s, there is a really, really wonderful program called the K2R program led by my colleague, Dr. Hannah Baldwani. So please check out that, and you probably will find it very useful. So I encourage you to all check it out. So today, the theme of today's workshop is AI agent for healthcare. So as you know, this is a really popular and hot topic these days, especially with the advent of the large language model in 2022. And we have, over the past 4 years, we have seen a dramatic increase in not only the available open source or closed source language models, but also a wide range of applications leveraging those large language model for healthcare, medicine, personal health management, and many other things. And in my lab, at the eHealth lab at School Information, we also have ongoing projects that are funded by both the Agency for Healthcare Research Quality, HRQ, and also National Institute on Aging on developing multi-AI agent systems to support patients' understanding of lab test results. The project is called LabGenie. So we have, over the past 2 years, we have gained substantial experiences in developing AI agents and also evaluating those AI agents and AI language models for a variety of healthcare tasks. So we'll be happy to share with you some of our research findings and also how we approach those problems in this talk. And but the essential goal for this one is not really to talk about our own research. It's really trying to give you some ideas about how AI agent can be built for healthcare and medicine. And so you'll be able to think about something that you probably have not thought before, that you can develop as a research proposal or collaborate with our team to develop research proposal or finding some potential collaboration opportunities. So again, agent is a very popular and very I would say like a buzzword. And this year in our FSU Machine Learning AI conference in the past month, if you were there, like our theme was agent, and we are really thinking that in the future, agent really will change the way we think, the way we do things, and also the way we really work, study is everywhere. So it's a natural evolution of language model will make very useful to our life because it's a combination of reasoning, logic, access to external information tools that are connected to generative AI models that can invoke concepts of agent. So this all, so essentially, I would perceive AI agent as a autonomous or semi-autonomous system that can evaluate your needs, input, and be able to assess what is the best model to call, or what are some external tools to use, or external resources to search for to answer or to meet your information needs or address your questions. And if we compare agents versus language models, we think that language models, if you have been using ChatGPT, like oftentimes in the interaction with ChatGPT, either is through like one-time input-output, you're kind of trying to interact with the systems, using that query-based, mechanisms. There's a search interface, look very closely similar to Google search, and then you just type a query or write a prompt, and the model will give you the response based on your input. And sometimes you can, in some of the modern systems, you can follow up with additional questions. You can ask it to do different things. And some of this exists in ChatGPT or Cloud or Gemini. They have actually already implemented some of this AI agent architecture in the backend. They just don't want to make it very clear for the end user to see. So there's a lot of things that happens internally. But essentially, models, if we compare like concept of models and agents, models are not supposed to call like external tools, and it's providing fairly naive logic layers implemented. So users can form prompt and simple questions and use reasoning frameworks either as chain of thought or React to form complex prompt to guide modeling prediction. And in comparison, agents is really trying to extend the capability of language models through connections with external systems and tools. It can manage like chat history to allow multi-turn inference and prediction based on user inquiries and decisions made in orchestration layer. So in this context, a turn is really defined as interaction between the interacting systems and agent. And the tools can be implemented in the agent architecture. So the process of building agents or multi-AI agent systems is really trying to figure out how to using these kind of building blocks that are serve on particular purpose to fulfill a particular task. And this is really important because in our real world tasks and situations, we oftentimes have to using very specialized agent to fulfill specific things. And this can ensure that each agent within the multi-agent AI systems, multi-agent systems can be relatively lightweight and efficient and effective in what they do. You can fine-tune those models based on your domain-specific knowledge and domain-specific tuning data set, and you can make sure that a model or agent within the multi-agent systems can fulfill the task the best way it can. At the same time, you can make sure that you can allocate, for example, the external sources using the retrieval augmented generation approach to answer those queries in a very specialized way. So this is really flexible and very powerful. So this one, give you some sort of more, I would say, schematic view about the difference between like agent and the models. So we think that model is fundamental building blocks. So models really trying to make sure that you can fulfill individual tasks in a very efficient and very powerful and a very accurate way. But agent allows you to build additional things on top of it to make sure that you can fulfill your needs by calling tools or by calling specific even if you have multiple models, maybe one model is better for inference, one model is better for reasoning, one model is better for retrieving content. You can actually decide which model to call when you have a particular task that are going to require those special skills and special needs. So there's a model layer which basically provides foundational language model that will be utilized as the centralized decision maker for agent processes. So these models used by the agent can be one or multiple language models of any size, either small or large, that are capable of following instructions based on reasoning or logic frameworks. And you can use either frontier models that are general purpose or proprietary models that are more safe to use, especially for medicine and healthcare. And oftentimes, people have concerns about using open source or like proprietary models like ChatGPT or Gemini or Cloud because your data will be potentially misused if they do something about it, right? But like if you deploy your own open source models in your own system and your data will be kept within your own systems, that typically is considered more safe and secure if you're handling more sensitive data such as healthcare data. And the orchestration layer will describe the cyclical process that governs how the agents take information, perform some internal reasoning, and uses the reasoning to inform its next action or decision. So this is a really critical piece that really figure out how do you want to split your task into multiple steps and be able to execute these steps in a logical way. And the tools are, powerful things because tools are really empower the agent to interact with external data or services while unlocking a wide range of actions beyond that of the underlying model alone. And this is really, as I mentioned, like extend the capability of language model. So thinking that, like language model such as ChatGPT is a foundational model that can do maybe 80% of things very well. But because of the particular task that requires very special knowledge, very specific data that are well curated, that you can make sure that it's not going to be generating any mistakes or hallucination or confabulations. And you can use that retrieval augmented generation approach to generate responses or answers to a particular question. And that typically will give you a better quality answer. But with multi-AI agent systems, you can even develop a more specialized agent that are handling the evaluation, the kind of using either the what we call grading by model type of approach, or using external tools to evaluate the accuracy, the credibility, the coherence of a response. So there's a wide range of tools you can use. So one tool, as we actually have been trying to use, is called DeepVal, which can evaluate the coherence and provide you with many scores that are fairly strong, fairly good, but it cannot review very complex medical knowledge thing. So you still have to use some of the retrieval generation approach or other approach to evaluate that. So there are existing systems in place. So here, this is another example showing you like what exactly does agent does. So for example, all of these things, you want to book a flight from Austin to Zurich, and the model will be able to take this input and thinking about what does it want to do to fulfill your needs, and then be able to call a particular website to find the flights that are available for this trip, and then giving you the responses. And how do they provide the responses to user in a way that really gonna be helping the user to find the information they need. So all of these are, talk calling potentially related to true calling and also response evaluation. So so in this way, the model could have guessed like an answer based on prior knowledge, but instead of using prior knowledge, they use external tool to find the real-time information. So this definitely will be providing you with more accurate, up-to-date information, especially for this type of information which are changing over time, every time. Because you can think of language model as a sort of a static model that if they don't use any search or tool calling, they will only have the knowledge back in 2021 when they used the initial Web Pro to train the initial version of ChatGPT. So this is an example of showing you how like Google has developed this co-scientist tool that is an advanced AI agent designed to function as a virtual search collaborator. Supposedly, you should be able to accelerate scientific discovery by systematically exploring complex problem space and enable researchers to find a goal, ground the agent in specific a specified public and proprietary knowledge sources, and then generate and evaluate a landscape of a novel hypothesis. Um, so um, so this is a kind of a general like workflow about like how they separate this different this scientific activity into different specialized agent. So there's a research goal and research describe a research goal along with the preferences, experiment constraint, and other attributes, and then generating a hypothesis. And the model is really trying to figure out how to how to like help the researchers. It could be like a fairly iterative process. So there's a generation agent focused on literature exploration, simulated scientific debates. There's a reflection agent focused on review of the web search result, simulation review, tournament review, and deep verification. There's an evolution agent focused on how to inspire new ideas from the other ideas and simplify the ideas and extend the initial research that are proposed by the researcher. And then there's also like meta review agent, proximity check agent. So all of the things are orchestrated and kind of supporting each other, and we call like AI co-scientist. Balu, do you have anything to add to this? Because you actually probably have better knowledge about exactly co-scientists
Yeah, I think
working.
this is the correct explanation, and they have some examples in the paper as well. They try to do some drug repurposing and other stuff, so they basically implement this in practical sense.
Okay. Okay. Yeah. So here's a link to this paper. So you're interested in like learning about how they did develop this or how this has been used. You can take a look at this reference. And So this is like think of a system as a research manager. So the AI first take a broad research goal and create a detailed project plan. And there's oftentimes in our experience, oftentimes you have to develop like a supervisor agent that will basically act as a virtual manager to delegate tasks to a specific member in this team. So they will be distributing resources or distributing tasks, and this manager supervisor will be able to kind of coordinate these activities that are happening within the multi-AI agent systems. So this way, the structure can be scaled up because you can always plug in a new agent in this framework, or kind of add new methods into this framework. And then for each of this agent, they can use a specialized trained fine-tuned model to fulfill that task. As you know, the best way to train a model is to using reinforcement learning with human feedback. So if you feed the model with a lot of gold standard user feedback data, the model supposedly should be able to using that information to to tune their parameters to make sure that the new responses generated for the new prompt are going to more accurately reflecting the needs and the style, the tone, right, for that particular conversation. So sometimes these models now allow you to work for hours. I've heard that people have used some of this agent system to let it run for like a whole night or something like that for multiple days to fulfill tasks. It's kind of just crazy that I recently also heard from my friend from Pittsburgh that he was able to just get a data set from from somewhere and just like pose a research question and then get the data to this model and then to this agent and then let it to just figure it out and let it run for like a night and come up with a full-fledged paper with very detailed all these methodology results and figures and tables. So I mean, they're like really afraid that all these AI models potentially in the future will replace a scientist like us. So I think it's really interesting to see all these crazy things happening to the scientific world and then being gradually changing our mind about how to effectively do research. So this is a example about AI agent in healthcare, and this paper was published also pretty actually early in the game. It was received in 2024 in August, which means that it was only received rather somewhat like within 1 year, 1.5 year, when ChatGPT became so popular, and they at this time they already have thought about using multiple strategies to generate responses to highly specialized healthcare tasks, such as determining whether a CT image or CT scan or medical image contain tumors, or what kind of tumor it is, either blind, either malignant tumor or benign tumor, how big it is, and whether you should be concerned about this. So they're already acting like real doctor or pathologist reading these images. So what they did, and at the time back then, maybe the technology is already kind of outdated for now, but at the time they already have medical guidelines, and they are transforming those medical guidelines into text embedding. So they can feed this text embedding into a embedding store. So this information can be used as a gold standard medical knowledge that can be used to answer some medical questions with LLM. So as a patient, you provide LLM with your patient case, and then the LLM's agent will be able to determine what will be the best strategy to respond to that patient case. For example, like determining whether there are tumor on the image and what kind of tumor, how big they are. And then, so they do it by looking at either using this knowledge base that are created by this team, or calling different tools that are available to them. For example, PubMed or OncoDB, those are the gold standard medical knowledge literature information. They don't do search on a general broad public website because those information, some of them are not credible and not quite useful. So instead, they're looking at using PubMed as a gold standard medical evidence. So OncoDB is an oncology-related knowledge base that provides also additional information that are curated for cancer and for oncology. And then they have also Python interpreter to interpret, like to do all those calculations about size, about risks, etc. And then they have also a radiology report that this GPT-4 can interpret radiology report, because radiology report at the time is like a text input. So at the time, I think GPT-4 was not able to take medical like image input. So they kind of using this radiology report, which is a manually written report from medical images. And then they also have a pathology AI, specialist AI, to do this analysis, calling specific tools and generating some of the responses like this that could provide fairly good interpretation to this medical information, to this medical data. So this is also showing you by calling this information, or calling these tools from external sources, they were able to generate more detailed responses for particular patient cases compared to generic ChatGPT-4 at that time. So GPT-4 was able to say, oh, for example, open, they cannot access or analyze text patient data, images, tools or databases directly, or blah, blah, blah. So there's a lot of things they say they cannot do. And then based on this one, they say, there's like potential, they perform lesion measurements, and based on the provided information, they can offer hypothetical and educational response. But if you're doing this agent systems, you're able to show you that there is a progression from February to June 2024. And this increase in size of lung metastasis as quantified by the segmentation tool results showing some increase in the overall area of lesion, and then indicating disease it's not adequately controlled under the current regimen. And then because they also know what patients are taking, what medication they're taking for the patients, so they can look at whether patients are, kind of having increased, sort of decreased size of tumor based on this intake, based on the medication. And then based on the genetic mutation information, they can analyze the genetic mutation to see whether this one provides some information indicator about future treatment decisions. So this certainly is much more sort of informative than the generic ChatGPT. We just feed model with pathology, with the radiology report and some very basic data. So this another paper was published in also pretty early, is about evaluation framework for clinical use of large model in patient interaction tasks. So this particular system is really trying to figure out how to translate case vignettes, which are oftentimes reported in the case report papers in the publication, into patient communication with doctors. So they are simulating, giving this patient case, what patient typically would say to a doctor, and what the doctor would typically ask the patient, and responses that can be also extracted automatically from this case vignette. So I think what they did is to trying to using this case vignettes to generate those patient conversations with doctors in a simulated scenarios, and then that human to evaluate whether this information makes sense, whether the patient agent is able to automatically pull information from these case vignettes based on the questions asked by the clinical model, by clinical language model, by clinical agent, and then how to kind of evaluating. So they can evaluate this with expert. So answering three questions: did clinical AI clinical model LLMs gather relevant medical history? Did patient AI agent hallucinate? Did it respond to properly to questions? Did it use medical terminology to describe symptoms? Is a greater AI agent reliable for evaluating equivalence of diagnosis, etc.? So this was also a paper published in Nature Medicine. And this one was published, I don't know, like, do you know where did they publish this paper? I don't see the
Actual nature paper.
Okay, so it's the main medicine
Main
like
journal, yeah.
Nature. Okay, Nature. Okay, I think this is also pretty new, right? It was published last year in April
Yeah.
by Google,
Google.
right? This team
Yes,
is from
Google.
Google.
Okay. Yeah.
So I think like a lot of these big companies, big tech companies, they also have a very big team doing all this kind of medical AI development because certainly medical AI is one of the most lucrative and profitable businesses for them to to tap in. So they get a lot of researchers and scientists and the data scientists on the team to develop those AI agent for healthcare. So this one is focused on diagnostic, how to using conversational diagnostic to based on to optimize diagnostic dialogue with patients. So again, they have multiple component within it. I'm not going too much detail. It's kind of very complex, but you can see that they really orchestrate a fairly complex architecture about how to process information, how to really provide medical reasoning, how to generate question answering to patients, how to summarize information for this conversation, and then using this information, how to provide diagnosis to patients. So they evaluate the different aspect of diagnosis, for example, the accuracy, whether the diagnosis provided by AI is able to be accurate, whether they can generate a good management plan, escalation recommendation, empathy, patient confidence in care, and then a perceived openness and honesty. So they can evaluate the AI responses to primary care physician responses. So PCP is people, the kind of how doctors would respond to these questions. And the AME is this AI system that Google developed. So they kind of compare all these six different dimensions using human review. And they found that at the time, for this particular evaluation, AME actually outperforms physicians in many of this, in all of these dimensions. With I mean this particular aspect is pretty similar, but obviously the management plan is an empathy level. For empathy and management plan, these two aspects certainly AIM is much better than the real human. And this one is another Nature Medicine paper focused on a large model for complex cardiology care. The aim is to using this like AME tool developed by Google to support clinical decision making for cardiology. So they also do a lot of patient cases, 107 patient cases, and evaluate them using all of this data generated by ECG, ECG, ambulatory care, cardiac monitor, all this information, and then feed this model to the data and let 9 general cardiologists to review them, providing their responses, and then let this tool called AME to generate this information. They kind of compare answer several questions to doctors because doctors may want to use some of this AI responses to help them with making decisions for their patients. So they are asking whether AI help with assessment, help with make you more confident. Did AI save your time? Did AI have any hallucinations? Did AI miss anything? And do you notice any findings on the raw imaging not mentioned in text-only report? So you can see like many of these responses are highly positive with strong results for yes, yes, for many of these questions. And this one is another one developed by Google. published also recently by this group and towards conversational AI for disease management. Yeah, they did really seem to be doing a lot of work with using this ME tool for generating diagnosis, decision-making process, trying to simulate the process of how a patient would interact with a physician, and getting questions responded, and also based on that information, how a doctor would be able to make that decision for patients on diagnostic results. So, and we have also helped with this. I when I was a guest researcher at NIH, National Library of Medicine, I also collaborated with Dr. Zhiyong Liu and Dr. Chao Jin there. And for this particular paper published also very recently in Nature Communication, we converted hundreds of clinical calculators published in PubMed into AI tools to automatically generate hundreds of calculators for patients. So manual creation supported by AI was used, and then they use also we also use some previous published system to convert patient notes into embedding space, and then be able to automatically choose a particular calculator based on what will be the most proper calculator for this particular case. And then once the calculators will determine eligible, they will be able to using this Python code to automatically compute this information. So some of these risk factors in these calculators can be pulled automatically from the published literature, and then the calculator actually this generation from this published literature to the calculator can be done automatically by AI. So basically, you just feed this information to AI, let it say, okay, let me please generate Python code for such information. So they will do it fairly accurately. And we compare using this tool, risk calculators, for answering some US MLE questions. So these questions are for board certification. So given a particular question and the multiple choice responses, whether using generative models, general models like ChatGPT generically, or using these agent MD models, whether we can accurately answer this question with confidence. So from the results, it did show that this agent MD model can be more accurate in answering those questions than just letting like ChatGPT say, okay, this is a question, this is the answer, please choose, make a choice. It's definitely much better. And then they can compare the performance of this many kind of calculators for human evaluation with human evaluation results. So if you're interested, please go and check out this article. And then I'm just going to give the floor to my colleague here, Dr. Balu Basudan, to go over more technical detail. But before that, I want to make sure that I don't have, do I have any questions so far? So I'm just, keep talking without really paying attention to questions or chat. Again, the purpose of this was just want to give you a more general brief discussion, a description about AI agent, and then I'll give you a more detailed view about how to develop this and how we develop this in our past work. If not, I will just move forward with Balu's part. So I stop share so I can share, right, Balu?
Yeah, I'll just try. Yeah, I think it's fine. So yeah, so I'll take the presentation from this part. So the goal of this presentation is to discuss about the practical building blocks and advanced frameworks used to deploy AI agents. So consider this slide as like the toolbox that what we are going to discuss. So these are some of the open source AI agent frameworks that we are going to discuss in the coming slides. So I have listed some of the examples here: Agent Development Kit, LangGraph, LangChain, Llama Index, Crew AI, and AG2. These are the widely used ones, and in our lab we are kind of focusing on these LangGraph and LangChain because these were some of the earlier open source versions of these tools and have like a good community support so that you can get a lot of additional features on it. And Agent Development Kit is from Google. It is now getting this momentum, and there are some other companies which are also open source with these frameworks as well. So as discussed from the previous slides, the idea here is an AI agent where basically it's a language model which is capable of accessing tools and follows a work plan. So how do we can practically implement in a local system so that it gets more secure and it's more like scalable. So at the conclusion of this presentation, what we are trying to convey here is the implementation workflows using LangChain and LangGraph, which can be operationalized through open source large language models. So the audience will be able to configure and execute API calls, which is called like application programming interface calls to interact with locally hosted large language model. So to give a little bit of context here, we are going to discuss some aspect of graph. So if you are new to this concept, graph in the concept of the programming, it is basically a map of interactions and it gives you the implementations of various algorithms. It can achieve state machines and implement these workflows. State machines in this context of AI agents are basically like what the current state of the AI model. It makes that AI model can decide what to do next based on the current status, and workflows in the sense that let's say something happens or went wrong in a stage 4, the AI can just go back to stage 2 and try it again. So this kind of a workflow mechanism implemented through graphs make it AI agents more powerful. And this particular package called a LangGraph I am going to discuss basically follows this kind of a methodology. So what we are discussing is LangChain and LangGraph, and it's application programming interface access for local language models. So the high success is because of this privacy and control. If we are basically in our lab, we are more focuses on health related data. So we are more concerned about the privacy and control of the data. So LangChain and LangGraph basically provide that to us. Key capabilities are building modular LLM pipelines using this particular frameworks. It is multi-step. You can do read, reason, and respond. You can locally host with API calls. There is no cloud dependency or any money or cost involved with it. It can integrate multiple LLMs like Llama, Mistral, Gemma, Mixtral, any open source model. This is very private, offline inferences, no internet or external data sharing is needed. So why these are more popular in the clinical applications? It's more private. It gives you the more control, flexibility, and integration to any type of data you can basically use. Its efficiency, and it can basically run hundreds and thousands of prompts locally if you have a more powerful system. We have a large GPU within our lab, so we are able to run hundreds of prompts every day without any cost by deploying these models. So to get example, as you know, the GPT-5, if you are trying to access in a GU environment, what you are getting is something like this. And current versions also support something like access to tools or web search, but this has to be by default off mode. You have to basically make it on mode, or you have to change it to each interactions when you're trying to do. But what we are doing here is more of like a programming way to interact with these models locally hosted without any host, without any cost, and no internet access is needed. So that's what I'm going to discuss in the coming slides. So the first one is LangChain. It's basically an open source framework built with the architecture of integrating with the local models. And this is the website. You can basically go there and see the various applications you can do with this. Um, so LangChain, the challenge here is that standard AI models like GPT or Gemini, they are brilliant individual locked in a room where they did not have access to this knowledge that you are known to be or you want to connect with it, but you just can do that with these models. So what is LangChain is enabling you to, as a popular framework that can act as a bridge between these AI models and the outside world. You can basically connect various tools that you are known to be or domain specific to the system. And one thing should be noted is this is useful for both open source models and closed source models such as GPT or Gemini. You can just use LangChain framework to interact with an API call to a GPT or a Gemini model. If you have access and paid for that service, then you can connect all the tools and methods that you are created on your own. That is also possible through this as well. So the bottom line is you are kind of turning an AI from a simple text generator into an active system. So give an example here. I am just adapting a recent study from Cornell. They are kind of reported the differences between these three open source tools and their taxonomies. So let's say a user is interacting, we can say real-time data we needed, like such as like a temperature in London, a prompt is generated and we are feeding that to any model. So the model basically looks for this data because it's a time-sensitive real-time data is needed. Always a tool is needed. So without this tool, this is the full pipeline that happens. But the LLM is enabled with these kind of tools that can retrieve the data from vector databases. Vector databases is basically the embedding data that are converted from any form of data that you have. It can search the web or API. It can keep on the conversation for multiple other interactions as well. So everything is enabled throughout this, and it can be locally hosted. And then once that informations are been extracted from these sources, the large language model is making the accurate real-time prediction here and then parsing it to the user output. So this kind of a workflow makes it more real-time, reliable, and also like trustworthy, like where it is actually getting the data from, you can basically trace back. So from these concepts, let's go to a real-world application we implemented here in our lab at eHealth Lab. So the case study here is the quality of the information generated by large language model within the context of lab test result comprehension. So as you know, patients get these lab results from their patient portals, but they may not be able to understand fully what's going on with these values. So oftentimes what patients, laypersons do, they just post these kind of questions to social media websites and expect some answers from people. So we kind of like evaluated how a large language model, if deployed, can be interacted and provide responses to these layperson's questions from a patient perspective, and then basically evaluated that against the already existing responses from a human in that particular social media. The paper is published in Journal of Medical Internet Research. It is getting some good citations from upon the publication as well. So we evaluated four language models at that time: GPT-4, Llama 2, MedAlpaca, and ORCA Mini, and evaluated in some existing widely used matrices to get that evaluation done with some clinicians. So as you know, we collected the data from like a publicly available social media called a Yahoo Answer. We filtered that and we found out that thousands of questions are posted by patients around their lab test results. These are very comprehensive questions actually. We kind of identified 500 manually by filtering that and then used a machine learning model package to look for the scoring of these questions. We extracted 100 top questions that are basically highly rated by multiple machine learning models. It's like an averaging out of the machine learning output. Then we selected 53 questions. So this was done early 2024, late 2023, early 2024. So we just started the evaluation and then looked for these four models capabilities. So as you know, GPT 3.5 and 4 were publicly available that time. We can basically access it through their web interface. But these other models at the time of that study were not easily basically deployable or accessible. So that's why where we just encountered this LangChain framework. I just discussed earlier. So I will show you how we were able to locally deploy these models and use it for our real world case study. So I will be discussing some aspects of this in the coming slides, but just we are just importing these LangChain frameworks, and CT transformer is a transformer based package which is implemented through C++ programming language. This can interact with any language model available through a transformer architecture. In the sense we are kind of configuring this. This is an added advantage of a locally deployed model. You can basically restrict how many tokens are generating. This is through max tokens. The repetition penalty, if the same word is repeated multiple times, you can restrict that. Temperature basically looks for how it can be generate like for the reproducibility. Top K is basically how many words should be used for the next word to be selected from. So the kind of the model is what trying to do is the next word prediction, and you are restricting that values. It can be from 10 to 50 based on the application. So yeah, so here what we are trying to do is we are basically using this locally deployed model. I will be showing how the model can be downloaded in the coming slides, but we are using a mid alpaca model. This was a model from Stanford at that time. There is a medically tuned alpaca model. We want to check there's a local model with a 13 billion parameter quantized into a 5 version, how this model can be used for our application. So we are asking the model once it is loaded to our system, the creatinine aspect of a patient. So the patient is providing some test results on the creatinine aspect. As you can see, the model was able to generate a result based on the interpretation of that value. It is providing some additional explanations of how should be followed based on this creatinine value. And one the next example I am performing it is a liver function test. So the patient had got a liver function test and basically provided a bunch of values and asking for some questions. So the model was able to interpret which is a liver function test. It is kind of calculating that ratio between AST to ALT. This ratio is an important indicator within the liver function test. It is kind of interpreting the value. Then it is kind of connecting that to the diagnosis that may occur. So basically, we try to see how these models such as medalpaca, a small model locally deployed, how it can like interact with a prompt that is more concerned about the lab test. We kind of evaluated it in multiple models and repeated this procedure for each of these models we wanted. And this slide shows that the differences between LLM generated response on the left with a Yahoo answer, which is highly rated from the human responses as well. As you can see, LLM generated is more detailed, comprehensive. It is going to provide some consideration, recommendation, and basically some future directions, whereas a human is kind of giving a very short answer. And the clinicians even found that some of these answers are not even correct as well. So we kind of considered multiple aspects of women's health, general health, cardiology, pulmonary, respiratory, kind of connecting all the triglyceride, FSH, creatinine in all the major labs that basically connected with these domains. And we kind of evaluated the performances. So as you can see, these are some of the standard metrics that used to evaluate the performance of the generated content. And we also, as you can see here, the word count, the character count is also a bit higher. Sometimes even GPT has around 2200 characters compared to a human answer. So the answers are comprehensive and detailed. Then we kind of did the evaluation with clinicians, even though the content is larger, is it clinically meaningful? So we kind of identified that here the lower the score is, the better. And clinicians kind of said that Llama, GPT, these are some honest facts introduced and provided some extensive explanation. So these are the comments from the human experts, the clinicians that did the study to evaluate that. And human answers were not helpful or very bad answers. So these were the comments from clinicians and the aspects. So kind of seeing that compared to a layperson, these models are kind of providing some good results in the context of lab test comprehension. So this was a real world study that we conducted using LangChain, locally deploying models. And I will be just now showing how it can be done in a larger scale. So I will put a link in the chat. This is a uh, uh, a link that we the source code is available in that kind of link. Yeah. So the here we are kind of trying to do that implementation aspect. So a popular framework of uh, the LangChain is a popular framework for these calls. So the first step is to you have to install this the LangGraph, the LangChain, the CT transformers into your the Jupyter environment. So here I am showing a Python interface based Jupyter notebook to implement and call these models. First step is the pip install. Once you did completed this installation, it's a very straightforward. Most of the time within a Python environment, you can directly install it. You are kind of invoking this one through LangChain community city transformers, and this is the additional thing here is the callback manager, basically for a parallel calling. You can basically do asynchronous parallel calling of multiple model invocations locally as well. Once you do that, the next step is to find out where the models are available. So I would recommend one of the good source to go is called Hugging Faces. If you are not aware of this, this is a globally recognized multi-model AI platform where you can basically get all the open weighted models. Lots of big companies and institutes release their models that are usable for other researchers in the community. It's a model hub. It has thousands of pre-trained models. It can support wide array of Python library do the API calls and locally deployable models. It's a kind of a collaborative and deployment environment globally used by all the data scientists. So it's just like you just go here, go to this and use your email to sign up for it. You will get an interface like this. You will be going to the data sets and models most of the time to get the data set and the model you are interested. And it's free and open source. So basically, you can download these models for free. So once you go to this particular model section, as you can see, a lot of tasks are provided here. It's for text generation, image to image, text to video. So based on your expertise and what you want to do, you can basically select it to filter it out. There are like thousands of models are available. As you can see, DeepSeek, QN, these are some recent models that are very popular in open domain. As you can see, the Microsoft is releasing some of their models. Facebook is releasing some of their models. So all the big companies, Google, Microsoft, Facebook, also releases free models here as well. Even OpenAI's GPT models are also available. GPT OSS 120 billion here as well. So basically, you can select which model you want to work with. I will be showing one example of how this can be locally stored in your system for interactions. So when you identify a model, you go to that particular models link. You can basically copy this to your programming environment. What you are seeing in the website will be files and versions. The files and versions give some README files, the configuration files, and what you want to do is to download a model that you want to interact, and each model conveys a different meaning. Here, if you are seeing a Llama 2 7 billion chat Q3KS model means this is a Llama 2 family open weighted model. It shows that it is a 7 billion model, indicating that this model has 7 billion parameters. It has chat or instruct name means it's a fine-tuned version optimized for conversational tasks. Basically, you can deploy this model, ask any questions you want. The model will basically provide an response to that. It can be a question answer dialogue, and it follows this instruction. And GGUF is a compact binary model. Basically, some of these bigger models are pretty hard to load in a small memory system. So they come up with an approach called GGUF. It's basically like a unified framework reducing the actual weights. And the other thing here is the Q3. Q is basically means quantization. So basically it's reducing the brain power, reduces the model size. So it's like in general, models are reported and trained with a 32-bit or 16-bit, but with some smaller performance degrade, you can still keep 4-bit or 8-bit model. It will be way lesser size in size. So you are not expected to have a big GPU RAM. So you can basically load some of the models even in your Mac system with 8 GB of memory. And there are multiple versions of Q series, and it can be also looked for small, medium, or large based on the size and the quantity. So once you identify which model basically suits you and for your task, you can download this model. So this is an programming interface where how you download this local model. You can kind of first install like a Hugging Face hub. This is the Hugging Face API call. You can make it, and using your credentials like your user ID and password from Hugging Face, You put that here, then you will be able to connect to the Hugging Face, and Hugging Face Hub is where you can download the models. You can directly show here. I am saving the model to a local D directory in OpenLLM's folder. You make the directory and kind of say which repo name is. So this repo name you can identify from here. This is the repo name. There is a copy button here. You can just click on it. It will copy the repo name. You make it the repo name and you can save the model, which model you want. You don't want to download everything because this is a 3 GB. If you try to download everything, it will basically overwhelm your system. So you can pinpoint which model you are interested. You just look for that 3 GB model. You just need that one model to interact and test it out. Once you do these two codes and locally download using this particular line of code, you can see something like this, and your model is locally downloaded. You will see a success, but like a response as well. So the model is kind of this one I am trying out here in the stock. Once the model is done, you can configure the model and try to interact with the model. Configuration, again, you are looking for the number of tokens, the repetition penalty, temperature, and top P. These were the one I discussed earlier. Then you are kind of looking for a CT transformer. You are giving the model to the path. It's a llama type model. You are using this configuration you did here, and you are just kind of making everything as a wrapper to this LLM object. Once that LLM is done, you come up with prompt. So I will be showing two examples here. The first one is a clinical note like extraction of a certain entity. So this is an information extraction task. I am instructing the model to extract some important concepts from a particular section in clinical note called assessment and plan. So this is a part where a clinician say some recent things going on with the patient and how to basically plan for the medical procedures. So I provided a synthetic data to the model as an input text, and I am invoking that LLM object we created earlier and getting that responses. So we instructed the model to look for an HTML kind of an extraction. So the model is identifying from this data the entities like what are the diagnoses mentioned, what is the medication, what is the procedure, what is the follow-up plan. It is giving a structured format, and as you know earlier, this is a very small model. It's just a 7 billion quantized model. Even with that, for this particular task, the model kind of excels in this, and it's giving us in a like a HTML version. So prior to if you are working with the information extraction, prior to these language models, in order to do a named entity recognition within NLP and information extraction, you may need a lot of training, deploy the model, and basically it was a lot of programming effort. But using this newer system and architectures, you can do a lot of things with the same system and in a very high performing fashion as well. So the second example is a summarization example. I am kind of asking the model to summarize a clinical note for me in 2 to 3 sentences. And I kind of providing this input text here. This is a progress note, an example progress note. And I ask the model to do a summarization. And from that, sorry. So from that data input, the model, again, we are invoking the llama model here, and it is giving a two-line summarization from this data that this female is having this diagnosis presented with what symptoms. So kind of like giving us a good responses for a locally deployed model. And the one cool thing about using like a local model within your system is the handling of multiple patient records. Let's say you are working with a case study of hundreds, maybe thousands of patients. You want to do testing on these models. If you are trying only the graphical user interface, one person needs to interact with the system 1,000 times. And if you are trying to change the prompt or optimize the prompt or the variables in that, you may need to do it again. But here using programming aspect, it's easier. You just need to store all the data into a JSON or a CSV format. You locally load that into a data variable. Then you kind of interact with this multiple times. You just create a prompt template, the same thing I showed you earlier. Then you do like this code base. This code basically looks for the nodes are the nodes of multiple patients I have stored. For each of these nodes, I am getting the patient ID to basically check the results are correct, get the clinical node part. Then I am kind of processing that node. I am invoking the configured LLM from the earlier configuration multiple times. And with this code, you can basically run hundreds of patient profiles. Whatever you want to do, you just change this prompt template here and put that prompt template here. You will be able to get the responses of thousands of patients and basically process that in your local system. This will process something like this. You can run multiple patients data for any task you wanted to do. So that's the other advantage of a locally like loaded system. It will create the responses like this. Yeah, so that is an example of how a LangChain framework can be used. It's more of like an interaction with a local system. You find out the system, what you want to work with from mostly from Hugging Face and get the model, locally download it, configure it, interact with the prompt, then uses JSON or CSV for multiple case reports or patient records you want. Then you just do that, maybe 5 to 10 lines of codes to work with any case, like the task you want with. Then I'm going to introduce a little bit of a LangGraph. So LangGraph is basically built upon LangChain we discussed earlier, but introducing a more expressive orchestration paradigm here. These LangGraphs are capable of modeling stateful, cyclical, and multi-agent workflows. So this is more of like an agent thing you can interact with. Even with LangChain, you can create sequence of models interact with each other, but LangGraph gives you a more like a strong, robust architecture where multiple AI agents can be deployed in a more cyclical workflow. So this follows a different architecture. It's called like a graph-based approach I like introduced earlier. It can give you, so the basic challenge here is it's some of the most of the models you work with are basically use ask and answer kind of stuff, but LangGraph is kind of an advanced tool built on top of this kind of a LangChain framework with for a multi-step AI interaction workflows. So it's basically gives you a loop kind of a cyclic architecture. It can plan task, try a solution, evaluate the work. So most of like a full autonomy here. And it's basically a production steady program. So basically once you implement LangGraph, you can deploy it in big environment. Currently in our lab, we are generating a model. I will be showing that, and we deployed that in Microsoft Azure within FSU ITS. So here the concept is graph-based approach. So there is a state, node, and edge. State is basically the current state of the particular AI system, and it can how it is deciding on moving to the next AI system or a response based on the instruction we are giving. The nodes are the functions that encode the logic. So what is the logic you want to try it with with an agent, and edges are the functions to determine which nodes to execute. Basically, from one node to another one, the edge will be going, but this edge is basically a function that provided by the instruction from the user. And it's durable. You can incorporate human in the loop. It's comprehensive memory. You can also show track the monitoring system where what's going on, what's actually working, what's not actually working, and how to do it. It's production ready as well. You can go to their LangChain's GitHub to look for how it is actually do the coding. So to give a little bit of a context, these workflows are allow you for parallelization. It can gives you routing approaches. We are more interested in the aspect of tools and rack systems. So what does this makes is like it will give more information because we are working more on the clinical side of the tasks and problems interested in. So here we are kind of integrating the memory, the domain knowledge, and the tools so that the model is not making any mistake. We are kind of making sure that through this LangGraph architecture. So in order to do that, there is a slight change from the previous one. We are using LangChain, but here we are adding LangGraph to this. So LangGraph basically gives you a start, end, and a state graph where you can kind of say which model to invoke at what point in time and how to interact multiple systems together. So this is all the LangGraph tools are in langgraph.graph. LangChain and LangChain messages are for interacting with the CT transformer model. Then there is like a Python inbuilt library for JSON data. This can be CSV or any data you are kind of working with. And the same thing, you are kind of invoking a model from the earlier thing. Here, the one slight difference is you are generating a model into a graph architecture. So you are making first model to read the clinical node, second model to run a large language model, and third model to show handle the output of the production. So once you have it, you can basically show how the model works. So you basically graph node, add node will make that kind of a node and edges. So here you can see these are the three major functions you are expecting the model to do. This can be a different LLM or a single LLM with multiple prompts. It's based on the architecture, and edge basically connects these nodes from start to this one, from this AI agent to this AI agent to this one, and then you making sure that it's finally ending. And once you do the compile, basically this system is alive. So it will start with this particular AI agent, followed by the second agent, and followed by the third agent, and finally the end. And it's a very simple example. What we are when you're basically implementing in for a specific problem, this can get pretty complex. I will be showing one example of that as well. So once you have a graph system added like this using LangGraph, you are have a multi-agent system in place. Then you basically do the same previous uh, example, but here we are working with AI agents with the LangGraph now. This will be invoked through this, and it will generate all the responses based on the same pipeline that I have shown earlier. So based on these examples, I can show you a real world study that we are currently conducting in our lab. So LabGenie is a web-based patient tool we are kind of developing in our lab at eHealth Lab at the School of Information, specifically designed to improve older adults' comprehension of lab test results and engagement in managing and acting upon their lab test results. So this is a more complex system. We are deploying 4 agents, a patient AI agent, a clinical AI agent, a grader AI agent, and a communication enhancement agent. This is a more complex system, but the architecture enables us to deploy this in a real world production environment with multiple models. I'll be showing this example how it is deployed in a LangGraph environment. So we are kind of invoking a supervisor. This is a model, and it has the ability to invoke all other models and do any error handling. If some model somehow is not working correctly and some not success image messages are there, the supervisor will handle that. Then there is like 1, 2, 3, 4, 5 different models are communicating each other, and the supervisor model kind of orchestrating the communication together. And this is a more complex system. In general, we are processing the data. We have a rack system stored in a vector database, and we are also enabling some web searches to specific points to medical literature. And the second agent is more of in the sense of some information generation, and the grader agent is more focuses on the evaluation. So we are integrating a lot of tools like deep eval, LLM as a judge, and additional tools that can do a lot of evaluation of the sense and scoring. Once this is being done, and some scores are way lesser and raises some alarm, our clinician will be as invoked. This is a human in the loop kind of an approach where the model can invoke to the data to the clinician. Clinician can review the data. So whatever we are presenting to the patient will be through clinician if it is well scored, and we are kind of making sure the data is safe, not overstating and additional expectations of the specific task. So this is how a real problem that we are kind of addressing and solving using LangGraph based multi-agent architecture. And all of these are, some parts are published already, some parts are in communication, and it's like multiple researchers are incorporating together for the deployment of this tool. So I can quickly show how it is done in our lab. So this is a LangGraph, Microsoft Visual Studio we are using. We are kind of creating a LangGraph here, and this is for the patient AI agent. And the full LabGenie code is around thousands of codes, but this is just a snapshot of how what we are doing here as a multi-agent workflow. So we are kind of adding multiple nodes. This is a supervisor, this is a patient profile researcher, and everything. We are kind of adding that into a graph architecture and invoking that model. And the visualization will looks like this. This patient AI agent itself is a multi-agent system, and the supervisor will basically do one task as profile parsing, followed by researching to look for the reference ranges of the labs in our ChromaDB based vector database through a RAG call. Then we have extractor to identify related symptoms. We have a conversationalist to make sure adequate symptoms are captured from the patient. And finally, an analyzer using certain Python calculators to make sure the reference ranges are correctly encoded and reported, and abnormal values are correctly identified. So this is a sequence of calls, and whenever an error occurred, this agent will give that message back to the supervisor. Then supervisor makes it the call what to do, or ask the model to rerun it, or see this basically invoking the model again. So everything is controlled through this particular supervisor, and this is more autonomous, and you can add more instructions to the model, basically allow the model to be more autonomous and powerful. So to summarize what we are discussing here in the presentation is the application of LangChain and LangGraph, deploying open source models for interactions and also a multi-agent system. So the user can interact with any LLM, but the added feature here is the chains or the agents through tools, vector databases, API search or web search. And through the LangGraph, you can basically do multiple nodes. The nodes will be interactive through multiple other nodes through the edges, and you just basically define the functions and the expected outcome from each of these nodes. You can create an architecture where this can be autonomously run and everything can be supervised by a different model. And finally, there is another thing we are not covering here due to time constraint is LangSmith. So this is more like engineering aspect. This is more like monitoring aspect. You can look for the traces, event logging, comparison engine, and all other dashboard kind of a monitoring things through LangSmith. So this is a highly used, widely applicable ecosystem from LangChain, LangGraph, and LangSmith. And these are some of the examples and code bases that you can explore with. And again, this is so the concept in an abstract way is development, orchestration, and observability. LangChain more concerned about as a simple chatbot or an agent prototyping. LangGraph is more like a multi-agent workflow with RAG and human in the loop. And LangSmith is more like a tracing or debugging and monitoring. And this is how we basically follow that notion like build, orchestrate, and observe using LangChain, LangGraph, and LangSmith. And this is a very good paper from Cornell. You can refer to this as well. So to give a final takeaway, we are kind of discussing that building large language model based health application require not just simple models and interfaces of chat. You need like an architecture such as LangChain or LangGraph, which enables you for a rapid prototyping, and it can give you like traces, access to tools, retrieval augmented generation system. All these are important aspects of clinical applications, which demands reliability, safety, and explainability. So we can start with, if you are interested in developing, I would recommend start something with the LangChain as a modular component. Try to download a model from Hugging Face, interact with it, try to do prompting, RAG, and everything. Once you are familiar with the LangChain, go for a more complex LangGraph system, multi-step agent kind of workflow, and then try to implement that. This is, you can basically integrate human in the loop, error recovery, and additional functions as well. So these are more clinically useful. If you are interested in health applications, this is a more robust kind of a pipeline. You can basically ground your output based on RAG or knowledge bases. You can direct the systems to look for certain clinical knowledge bases, such as OncoDB, Medline Plus, or Mayo Clinic resources. and more structured outputs can be generated. Everything ChatGPT can do, these models can do as well. And you can prioritize safety, like readability, and then clinical relevance, because if you're trying to do something with the patient facing as well. So these are some of the concepts and some of the introductory codes that you can explore with if you're interested in developing a multi-agent system. Happy to take any questions.
So we also do have, while we're taking questions, I also do appreciate if you could provide us with a feedback. Also, we have this feedback survey. So if you have any thoughts or feedback about this workshop in particular, please scan the QR code to to get access to this particular survey, and also the link of this QR code of this link I also posted here for everyone to use. Any questions about anything that we have talked about today? Yes, I see one hand by Satish.
Yes, hi. Thanks for this great presentation. I see a lot of research and a lot of work being done in the background. Really, lot of takeaways from me personally from this session. So I have a few questions, like some of it related to the GPU. So Balu, you said you were running it on your local GPU. Like, what kind of GPU? If you can give some technical specification on that, like, is it hosted within the FSU? Like, how much VRAM did it have, and what kind of inference speed did you observe? Like, for each request, you were able to get the response faster, or had some latency? Yeah.
Yeah, so this is an A6000 from Dell, and this GPU RAM is 128 GB.
Yeah, calculator is from NVIDIA. It's not from Dell.
Yeah, this is NVIDIA A6000, but the architecture is NVIDIA A6000 GPU with 128 GB RAM.
Yeah.
And we were able to basically work with, we are kind of using the reason models as well. So up to 7 billion to 13 billion, the model will give you responses in 1 to 2 minutes.
That's great. Like, do you use any quantized version of the model, Balu?
Yeah. It's a Q4 or Q8 most of the time, but we are kind of using the larger versions as well. But mostly it will be Q8 or Q4 or Q8.
That's really great. Like, did you see any performance, like the quality of the clinical outputs, like were you able to evaluate when you used a quantized version of the model compared to
No,
the?
not much actually.
Okay.
Our focus is more on, like, this is like a clinical data, like a patient
Right.
vignette. I did not give more. This is more of a technical side of the presentation, but the clinical data is processed in a way, and we are expecting the model to do something like differential diagnosis generation or responses summary, those kinds of things. And we see most of the time, even with a Q8 or a Q4, the model kind of keep that performance quality. There is sometimes some models like Llama may give you very like non-related data, so we just rerun on the same prompt. That can happen, but it's just like in, I would say, 70-80% of the time the responses were expected, and it's a good quality.
Okay. Thanks for answering that. I might reach out to you later. I have
Yeah,
more
sure.
questions.
Yeah, you can go to the CTSA website, or my email is also available. You can just search. I can
Yeah,
put it in the
GPT.
chat.
Yeah,
I can
I'll put
put
in the
it in the
chat.
chat.
Yeah.
Yeah.
Yeah, I can put in the chat too.
Yeah, you can just switch to
Yeah,
my.
our lab, we have actually been doing this research with open source models and evaluation models for a variety of different house tasks, such as causal reasoning, question answering, also evaluating generating new data sets for benchmarking AI models in the past 2 years. So I'm just gonna copy and paste some of these papers we have either published already or have been deposited into ArcSieve or medRxiv, so people can take a look at these papers. Yeah, we're open for collaboration. If you are interested in kind of collaborating with us, especially on health-related problems, and please feel free. We're trying to limit our kind of research scope within healthcare, biomedicine, and so if you're in this area, would like to collaborate on anything that might be interesting to explore, we're happy to chat. Any other questions? And Balu, maybe you can also briefly talk about some other open source or closed source like tools for building AI agent, in case people are interested in know more options. For example, big tech companies, they also have releasing new
I had a
platforms.
slide in the beginning, so maybe I can quickly go. If you go through that slide, I have put it in the. If you go,
okay.
in the beginning, like 21 or something, 22.
Okay.
Yeah, maybe here. Yeah, this 21. So these are
Okay.
the
Yeah.
other ones if you are interested. So we are focusing on LangChain, LangGraph because we started working with it. It was one of the earlier systems that were open sourced. But Google's agent development kit is there. They are also getting some momentum, and then Llama Index, Crew AI, and AG2, and these were the one listed in Google's recent white paper as well. So on the right side, these are the major ones listed by Google as well. So that's why I introduced those ones.
Mhm.
And I hope everyone gets that code in the link. When I was trying to paste it, it shows that admin access or something. If you are interested, there is a posted link there in the GitHub. So we did a similar workshop for the same data.
Yeah, I do see the link posted on in the chat already. It's just they warn you like we cannot upload files to the chat, but I do see the link you posted that was used for our previous workshop at AMIA.
So
Yeah,
you will
I did
get
see that.
a sample data and these codes there. You can just work it out on your own. And if you have any questions, just email us.
Sure. Yeah, but again, I think we're approaching the end of this time. And thank you so much for everyone for joining today's webinar talk. And we will also post this webinar talk to our CTSA Bird website. So at CTSA Bird website, we have a particular page for informatics workshops and training materials. So if you still want to kind of come back to this and learn more about this particular presentation, you can go to this link. Last month, we also had a talk about how to use electronic Hopper data to build prediction models. So that was also has been posted on the page as well. Again, thank you so much everyone for joining. Glad to see you all and see you next time. Bye bye.
Bye bye.